My name is Weil from Inktank, and today I'm going to talk about the Ceph distributed storage system. Just a brief outline of what I'm going to talk about, a little bit about why you should care about another storage system, sort of what Ceph is from a high level, how it works, what it does. I'll talk a bit about the distributed object storage layer, and specifically about some of the interesting features of our object API that talks to that distributed object store. Then I'll talk a little bit about the distributed file system that we built on top of that, and some of the interesting things it does, and then finish up with a little bit about who Inktank is, why we work on Ceph, and why we think it's important. So to begin with, why should you care about yet another storage system? You've heard many of these talks during the course of the conference. And I think there are a few reasons. One is simply a matter of requirements. People have very diverse storage needs. Some people need object storage because they're building the next Web 2.0 application. They're going to dump a bazillion images into some big distributed server farm. Other people need block devices for running virtual machines and so forth for their public or private cloud infrastructure. Or maybe they want to replace their legacy SAN that's too expensive. Other people need a shared POSIX file system because they're running legacy applications or because that's what their users demand and so forth. And other people are doing big data types of things where they have structured data and they don't frankly really know what they want. Maybe it's file, maybe it's object, and it's maybe not particularly clear. But sort of common across all of these things is that people really need systems at scale. So when you're building out a large infrastructure for the enterprise, you need to be able to incrementally add nodes to go from terabytes to petabytes to exabytes. Typically, you want to be able to run on heterogeneous hardware, so you don't have to buy all the same box from the same vendor, but you can sort of grow as time goes on. And as a result, you need to deal with issues of reliability and fault tolerance in sort of the key design. The other thing that's important in these types of systems is the amount of time that you spend administering them. In particular, the ease of administering dozens or hundreds of individual appliances can be prohibitive, and so you'd like to have a single unified system that you can sort of work with as a single unit. And that means you want to avoid tedious things like manual data migration. As you add new nodes to your system, you don't want to have to move data around and so forth. You want the system to sort of figure all this stuff out for you. And painless scaling, of course, is a key part of that, and that includes both expansion as you deploy new servers and also contraction as you take old racks of machines that are old and failing and wired incorrectly or whatever, and rip them out of the system and have all the data sort of spread to the new nodes and have a sort of seamless migration as that happens. And finally, of course, cost is very important. Ideally, you want cost to be a linear size, a linear function of the size of your cluster or your performances, or as close to linear as you want. You don't want the sort of exponential curve that you get when you're buying more expensive options. You would like incremental expansion, so you don't want to have to deal with forklift upgrades. And ideally no vendor lock-in, and so you can have a choice in what kind of hardware you run on and what kind of software you run on. And so what a lot of organizations are demanding is really an open source solution that they can run on whatever hardware they choose. That's sort of the ideal situation, of course, from our perspective. And that obviously demands the question of what exactly is Ceph? Well, it tries to address many of these concerns. First and foremost, Ceph is a unified storage system. The idea here is that we can deal with multiple interfaces to storage, both object storage using our native APIs or RESTful APIs compatible with S3 or Swift. You can also store virtual disks or block devices with features like thin provisioning, snapshots, cloning, that sort of thing. And finally, there's a POSIX distributed file system, so you can actually store files and directories and so forth in the cluster. And you do this all with the same unified storage infrastructure. So it's sort of at the API stack at the bottom, you have this component called RADOS. That's a reliable distributed object store. And that's the thing that scales to thousands or tens of thousands of storage nodes and makes sure that all your objects are replicated across multiple nodes. It sort of dynamically moves data around as cluster state changes and sort of handles the reliability and scalability key pieces. And then on top of that, you can sort of talk to that distributed object store in a number of ways. You can use the native LibRados API to just, if you need sort of a raw object storage for your custom application or something. There's this RADOS gateway component that sits on top of that API that gives you S3 and Swift compatible object storage using RESTful APIs. There's an RBD component that gives you a virtual disk that's essentially a logical disk that's striped over objects that are then stored in this distributed object store and shared, reliable, all that good stuff. And finally, there's a distributed file system that also leverages the reliable storage abstraction to build a sort of higher level service where you have POSIX semantics with files and directories and so forth. Ceph is open source. It's licensed under LGPL2. It's a copyleft license, but you're free to link to proprietary code, so it's very easy to sort of integrate into other projects. And unlike some other projects, there's no copyright assignment, and so it's very essentially the project copyright isn't held hostage by a single company that can then relicense it and extort money and so forth. So tends to be very friendly in that sense. There's an active community of users and developers, and there's also commercial support available now. Ceph is a distributed storage system, and what we mean by distributed is that it's designed to go to data center scale. So you can imagine tens of thousands of machines in a huge data center, all participating in a single aggregate storage pool that you can leverage using your applications without having to worry about the details of where your data goes and so forth. So it can scale a single cluster all the way from terabytes up to exabytes. It's distributed in the sense that it's fault tolerant. There's no single point of failure. Any particular host or daemon or node in the system can fail due to a software bug or a power outage and so forth, and the system will keep your data available throughout that. It's designed to run on commodity hardware, so we try to take advantage of whatever you have available, whether it's hard drives, SSDs, NVRAM, whatever it is, we can generally consume it. And we try to make the system self-managing and self-healing, so that when you have a system that builds an entire data center, your sort of OpEx costs aren't proportional to the size of the system. So you manage it as a single unit, and for the most part, the squirrels sort of behind the scenes deal with all the details of moving data around using software. So the Ceph distributed object store is based on an object storage model, and the basic idea is that you have some number of pools of storage that are sort of logical collections of objects. They're independent namespaces and collections, and for each pool you set some replication policy. For example, you want 3 copies of every object. And then inside each pool you have bazillions of objects, and each object consists of a blob of data, so some number of bytes similar to a file, some attributes similar to extended attributes. And you can also store in an object a key value bundle. So think of it as a sort of a small NoSQL table or a Berkeley DB file, where you can sort of have sorted key value access to an object as a sort of container for multiple keys. So the question is, why do we start with objects? Why do we build a distributed object store instead of a distributed file system first? And the first reason is that objects are much more useful than starting with blocks. So in contrast to a disk drive where you have blocks that are sequentially laid out and you can't really name them and you have to deal with all the allocation details and so forth. Objects are named, they live in a single flat namespace, they have variable size, and they give you sort of a simple API with very rich semantics. So they're very easy to program to build some higher level service on top of this basic storage abstraction. But more importantly, objects are much more scalable than files. So in contrast to a directory hierarchy that's very difficult to sort of chop them to pieces and distribute across thousands of nodes, objects have no sort of relation to each other, except for the fact that they have unique names. And so it's very easy to hash them across bazillions of nodes and have the system sort of intelligently manage that without having weird interdependencies and locking and strange problems like that. So you can imagine the general goal of a system is to have some human interacting with some set of storage systems. And you want it to scale so you have lots of disks, and so they're all sort of going through a computer. The problem, of course, with this is that you actually have lots of humans, or probably something more like this, and it's obviously this sort of server, and this sort of typical client-server scenario becomes a bottleneck. And so what you really want to do is have the consumers of storage, be able to talk to lots of different storage devices directly without having to do it through sort of a single bottleneck. So that's what the Ceph architecture does. So sort of a slightly different picture here. You start with a number of disks. On top of each disk, you slap a local file system, typically Btrfs or something like that. You can also run on ext4 or XFS, although Btrfs is sort of where we're going in the future. And then on top of that file system, you have object storage daemon, a Ceph object storage daemon that manages that particular local set of data, and then communicates with the other daemons in order to provide a higher level abstraction. And then you typically have a whole bunch of these inside a node. And then you have a bazillion of these to sort of form your larger storage cluster. You additionally have some number of these monitor nodes that are responsible for essentially herding the cats. They deal with cluster membership in the state. They use Paxos to sort of make sure that we know who is participating in the cluster and what your role is at a particular point in time. But these guys aren't actually involved in any of the data path. They're only involved in sort of cluster management, cluster state. In contrast, these object storage daemons, you need at least 3 of them. Typically, you have hundreds, thousands. Each one is serving up some local piece of storage and contributing it to the aggregate pool of storage for the entire system. And the idea is that we want to make these OSDs as intelligent as possible so they can do most of the work of sort of dealing with this distributed system. And so that the end result is that you have your user who's essentially interacting with the cluster as a unit. It doesn't care that it's actually made up of 1,000 different nodes, but the cluster sort of handles the details of where data goes and how it's distributed and so forth, and that is hidden behind a nice, clean, logical storage interface. One of the key problems in designing a system like this is deciding how your data should be distributed. So our requirements are pretty simple. We want all objects to be replicated some number of times, and it's totally tunable, but usually 2 or 3 is what people choose. And we also want those objects to be automatically placed and balanced in a dynamic cluster, because these systems are going to change over time as disks fail and new storage is deployed and so forth. And we also want to consider the physical infrastructure. So we want to make sure that if we're replicating objects, we place replicas in different racks of the data center so that a single power circuit failure won't affect the availability of my data, for example. So there are sort of 3 basic approaches that you can take for deciding where to store data. One is to pick a location and remember where you put it. And so when you come back a week later, you try to go back to the same place, and hopefully your data is still there. The problem with that is that if something happens, say that a host failed or a rack failed or so forth, that won't actually be the case. So that's sort of not a very good strategy. A more typical approach is that you pick a location for the data and then you write down where you put it in some sort of metadata server index or something like that. And then when you have to go back and read the data, you look up where the data should be stored. It tells you which server to go to, and then you go to that server and you find your object. That gives the system control, so it can actually move things around, but it has this whole index that it in turn has to be able to scale to huge index sizes and becomes a problem. So a very different approach is to use a hash function to determine where your data should be stored. So essentially you calculate a location based on the current state of the cluster, and that tells you where to store it. And then when you read it, you perform the same calculation, and it'll tell you where to go to find it. And to do this, Ceph uses a function called crush. It's a pseudo-random placement algorithm that is a fast calculation for where to store data. There's actually no lookup involved, so we don't have to bother with maintaining this index, and we just calculate the result whenever we need to find it. It's a repeatable deterministic calculation, of course. But the key property is that it maintains a stable mapping, so that if you have 100 servers and you add 1, typically 1% of the data is going to move to that new server, so you don't have this sort of random reshuffling that you would have with a naive hashing algorithm. And the other key thing with Crush is that it gives you, it's very flexible in that you can specify rules that determine how your replicas are placed in the cluster. So for example, you can specify that I want 3 replicas, I want them all to be in the same row of the data center so that my replication doesn't traverse my spine network core routers or something like that. But at the same time, I want the replicas to be separated across different racks. And you can specify these constraints, and this calculation that it does will obey those sort of basic properties so that you get the layout that you want without having to have an actual table to store the results. So in a bit more detail what this looks like then, you have essentially a pool of a bunch of objects, and you hash the names of the objects essentially by the number of what we call placement groups. Essentially we're sharding this logical pool into a bunch of different pieces. And this gives us some number of placement groups that are rainbow colored, if my animation worked correctly. And then for each of these placement groups, we feed it into the Crush algorithm, and then that calculates where in a cluster those guys are going to be stored. And so you get this sort of declustered approach where your placement groups are sort of randomly scattered across the cluster. But in this particular example, our rule specifies that we will always choose 1 node from the top row and 1 node from the bottom row. Say they're different hosts or different racks or something like that. And the way that this works is that the distributed object store, RADOS, periodically publishes what's called an OSD map. That's essentially a snapshot of the current state of the cluster, which OSDs are participating, what the Crush algorithm that's specifying how data is mapped onto those nodes, and all the current IP addresses and so forth. And using that particular map, we can calculate where any particular object or piece of data should be stored in that storage cluster. The object storage daemons then are responsible for safely replicating the data in the storage cluster. And if there's a new map published over time because there's, say, a node came up or came down, those nodes are responsible for using sort of peer-to-peer protocols to migrate data to the new location as specified by that map. And they use gossip protocols to efficiently share these map updates and so that they can sort of stay in sync about what the current distribution of data should be in the system. This is a very decentralized, distributed approach that allows massive scales because you don't have any sort of central coordination aside from the fact that you're publishing maps that says which nodes are up and down. Nobody's having to say, you take this piece of data and move it over there, but instead sort of the leaf nodes, the OSDs can do that on their own because they all have a shared view of reality based on these OSD maps. So then a client then also gets a copy of this map, say it needs to store a particular object. It can do that Crush calculation and it'll know that it's in the green placement group stored on these 2 nodes. It has sort of complete knowledge of where all data is stored by virtue of this mapping algorithm. What happens then if you have a node that fails? Say we lose a node with the yellow and the orange. In that case, the other OSDs that are replicating those placement groups will realize that their peer went down essentially because they got a map update. They can see that the replicas are no longer there. And the new they'll identify who the new home is for those data objects, and they'll actually migrate them. And this is a sort of fully peer-to-peer process, so there's nobody is actually having to do this for them. So again, it scales very well. And then a client, if it needs to read that object, it'll get a new copy of the map, and it can go to the new location and find the data where it should be. So LibRADOS is sort of the low-level API that talks directly to this distributed object store. It's got C, C++ bindings, Python, whatever. It's very easy to consume. And so essentially, you can take an application, link to LibRADOS, and it can use the native protocols to talk directly to these bazillions of storage nodes in parallel and sort of have full access to the raw capabilities of the cluster. LibRADOS also provides a number of other interesting features that make this particular object API very interesting to consume. One of those things is atomic transactions. So the client operations can actually contain multiple operations in a single request, and those will be sent to the object storage node, and it'll apply all of those sort of atomically. They'll either all succeed and commit atomically, or none of them will commit and it'll fail, which is kind of nice. So this gives you atomicity, which is very helpful. You can also do conditional requests. So you could send a request, for example, that says, make sure this x adder is equal to 1, and if so, then apply this operation, but if it's not, don't do anything. So you can do sort of atomic compare and swap type operations, and that's all mediated by the object storage cluster. The OSDs also support a key value API for individual objects. So instead of storing just a sequence of bytes like a file in an object, you can store multiple keys and values. It's based on Google's LevelDB implementation, which is pretty nice. It's sort of the big table SS table design. Gives you efficient range query insertion, that type of thing. So you can insert, update, remove keys, and you can also, the key thing that this allows you to do is sort of efficient read, modify, write type workloads, where you can say, for example, that I want to just remove certain keys, and that operation will happen efficiently on the OSD without having to read the entire object over the wire, make some small change, and write it out again. So for example, the Ceph distributed file system leverages this capability to store directories in objects. So instead of having to read the whole directory in and make a small change and write it out again, it can just tell the OSD to remove this file, and they can do that efficiently. One of the other interesting things we can do is what we call watch notify. So essentially, you can establish sort of an interest or watch on a particular object in the object store. So multiple clients can sort of observe a particular object, and then they can send notify messages to each other. So you can use sort of an object as a meeting point and a message communications gateway for clients to coordinate. It allows you to do similar things that you might do with sort of Apache Zookeeper, but using this distributed object store as sort of the basis for doing that type of coordination. So an example of what this actually looks like here are a number of different clients, each sending watch requests to an object. They get a commit that says they've registered that watch interest in the object. And then later, if somebody sends a notify request, that notify gets distributed to all different clients who have watched it. And when they all acknowledge, then you finally get a notify acknowledgement that says, yes, I've notified everybody who's watched. And so you can use this for a number of different things. What we use it for, one example is the RADOS gateway component that's doing the S3 gateway. Uses it to manage its own cache consistency. So it sends invalidate messages, essentially, to invalidate entries out of its other RADOS gateway instances caches, because you typically deploy like 100 different RADOS gateways and behind a load balancer or something, and they're all caching things, and so they use this to keep their caches coherent, which is pretty useful. One of the more exciting things that you can do, though, is you can actually implement what we call RADOS classes. So you can dynamically load a shared object into the OSD that implements new functionality for objects that's based on existing functionality. So for example, you can implement new read methods on these objects, if you will, that will run arbitrary code, essentially. And then for read requests, they'll do some transformation, give you a response. Or for write, they can do some sort of higher level mutation on the object and then atomically commit that to disk. So some simple examples of this would be like a grep class could scan the contents of an object and tell you whether there are certain matches or return only certain records from it. Or you could calculate a SHA-1 of an object and return it. If you were building a Flickr application, you could send a request to an OSD that would filter out the red eye and write the object back out to disk or generate a thumbnail, that sort of thing. And without having to read all this data over the network and make a small change and write it out again. So there's also moving on, I guess, there's a RADOS gateway component that's built on top of LibRADOS that gives you S3 and Swift compatible API access for people who sort of want a drop-in replacement in their own infrastructure for applications that are targeted towards S3 or Swift interfaces. That's built on top of LibRADOS. It's relatively straightforward. There's also a RADOS block device that gives you a virtual disk. Essentially, we just take a sequential disk and stripe it across lots of objects and then distribute those across the cluster. That's pretty well integrated and works pretty well. So you can imagine essentially taking all these OSDs and distributing little blocks across them and aggregating those into a virtual disk and then attaching that to a computer or multiple VMs more typically. So this is has a number of nice things. You can do snapshots on these virtual disks. It's linked directly into QEMU, KVM virtual machine framework, so you can have a virtual machine that's backed by the Ceph cluster without any kernel support. There's also support in the Linux kernel though, so you can map like a dev RBD device that's backed by the Ceph cluster. And you can also, one of the newer features you can do here is you can take an existing RBD image and you can clone it to create a copy on write clone of that. So for example, you might have an Ubuntu 12.10 image that all your VMs are based off, and you can clone a bazillion of these and then boot them up immediately without waiting for all that data to be copied into a new image before your VM can start up, which is an attractive feature for cloud infrastructures. So again, you're taking lots of objects, you're sort of linking them through the librd library, integrating with some virtualization container and giving a virtual disk that's consumed by a virtual machine. And of course, because we're dealing with shared storage here that's reliable and so forth, you can also do nice things like a virtual machine by migration, live migration. You take a running VM and move it from one host to another because they're talking to the shared storage backend, and that all works pretty well with KVM. And of course, you can use the native kernel block device to map a dev RBD device on a regular host and put ext4 or whatever else it is on top of that. But probably the more interesting piece here, as far as complexity, is a Ceph distributed file system. It's probably about as many lines of code as everything else combined, because file systems are complicated, even when you start on an object storage foundation, essentially. So, and the key idea here is that clients who are mounting the file system will talk to metadata servers to deal with issues related with the file system namespace, so for resolving paths and traversing the hierarchy and so forth. But then when they actually need to read and write file data, they can talk directly to the object stores, the OSD nodes, to read and write from the object that stores that file's data. And so this allows the data path to be highly parallel and distributed and scalable and so forth. And then we just have to deal with having a file system hierarchy that's spread across multiple metadata servers. And so that's really where the complexity here comes in. So we have these new metadata server components. These are Ceph MDSs. They're responsible for managing the POSIX file system hierarchy, dealing with all the file metadata, owner, mode, UID, GID, all that good stuff. They store all of their metadata in RADOS again, so we're leveraging the fact that we already have this magical, reliable, distributed, scalable storage abstraction. So these are really just daemons that are caching lots of stuff in memory and then writing everything out to RADOS on the back end. And of course, they're only necessary if you're using the Ceph distributed file system. If you're talking to just the object store, then the metadata servers don't even get involved because those objects are trivially parallel and all that good stuff. But building the distributed metadata server was an interesting design problem. Part of it was due to the fact that sort of the legacy metadata storage approaches are sort of a disaster. So you typically have a file name, it maps to an inode, which is stored in some other table, and then that has a block list, which is all the blocks on disk that you have to go look, and then you find the data. So there's this multiple levels of interaction before you can actually read a file, which is kind of sort of annoying. And the inodes are stored in a different table. Often the locality isn't very good, and the inode table gets fragmented. So even though you're looking at sequential file names, the inodes are scattered in random places on disk, and things get fragmented, and it's lots of seeks, and it's difficult to partition, right? You have your directory structures over here, and then you have your inode tables over here. And if you want to spread things across multiple servers, how do you make sure they're on the same node? And it's a nightmare. So Ceph stores metadata very differently. The first observation is that block lists aren't necessary. We're storing our file data in objects. Objects are variable sized, and we can name them. And so we can just name the objects that are storing the file data as the inode number, maybe with a block number. And so we don't have any block metadata at all. Ceph inodes are very small and relatively compact because basically fixed size. The other observation is that inode tables are usually useless because you only have a single file name linking to a single inode most of the time. And so in those cases, we can embed the inode directly in the directory that refers to that file. That means that in Ceph, we just store an object that has the contents of a directory. It has all the file names, and most of the time it has all the inodes that those file names refer to. So we can do a single IO to the OSD, read a single object in, and we get all the file names for a directory and all the inodes. So we can do things like ls-al very quickly. And we leverage the key value objects on the back end to make this all efficient and easy to manage. The real challenge, though, is that we have this one big tree one big file hierarchy, and we have multiple metadata servers. So like, how do you make this work? And what Ceph does is we sort of dynamically carve up the tree hierarchically. We'll just take big chunks, subtrees of the overall directory hierarchy, and we'll assign them to different metadata servers based on the current workload, based on how busy those subtrees appear to be. And we can sort of arbitrarily do this. So they have all the logical complexity to migrate subtree management between metadata server nodes and sort of arbitrarily partition it across metadata servers. And what we call, an algorithm we call dynamic subtree partitioning. And the nice thing about this approach is that it's scalable. We can take a hierarchy and we can sort of arbitrarily carve it up into little pieces. So that's nice because we want to be able to have hundreds of metadata servers. The other nice thing is that it's adaptive. So the metadata servers are sort of monitoring how busy the file hierarchy it is that they have cached is at any point in time. And if they decide that they're overloaded, they can sort of take about 20%, it's about this big subtree over here, and they can shunt it off to another metadata server. And this is based on the current workload. So if your workload shifts later and suddenly you have a total different file set that you're working with, the metadata server will adapt by splitting that file set into smaller pieces and distributing it across the cluster so that you're sort of always utilizing all available metadata server resources. It's efficient. We use a subtree-based partition so that we preserve locality within the workload. So most applications are working within a single directory or nearby region of directories, and so those tend to be focused on a single metadata server. We get all the caching effects and locality, and renames tend to be local and all that good stuff. And finally, it's a dynamic cluster. So we might have 3 metadata servers right now, but when load goes up, we might add an additional metadata server to sort of expand demand. When a metadata server fails, another one can take over by replaying its journal and rejoining the cluster. And so it's a very dynamic environment. One of the challenges, though, is dealing with metadata I/O. So metadata tends to be very small. It's updated very frequently, and you sort of want to avoid a situation where you have lots of small writes to the object store because that's, no matter how well you optimize it, it tends to be a nightmare. And so the way we approach this is to view the Ceph metadata server as sort of a big cache. Essentially, you have client requests coming in on one side, and you want to make sure that you have fewer reads and writes coming out on the back end to the RADOS object store that's sitting behind it. And so we want to reduce reads by doing prefetching and keeping a nice cache, very big cache. You want to give them lots of memory. And we want to reduce writes by consolidating lots of updates into a single sort of transaction that we then send out the backside. And the way we do this is by maintaining a very large journal or log for each metadata server. So the idea is that it's essentially a large sequential file or log or whatever you call it. We stripe over objects in the object store. And then we essentially, whenever there's an update to the system, we write it out to the journal, and then at that point it's durable and committed and we can move on. But we end up with sort of 2 tiers. We have all the recent updates get consumed by writing things out to the journal, and then later when the journal gets big and we start trimming things off the end of the journal, we then take all those updates and we push them out to the long-term storage, which is the per directory objects that store the file system hierarchy on the back end. And so the nice thing, of course, with a journal is that you have very fast failure recovery. So if a metadata server crashes, you can just read it in. But the more important thing is that as the journal grows over time, you notice an interesting effect where the things that you write at the beginning of the journal are always sort of dirty. Those updates exist only in the journal. But metadata tends to be updated multiple times repeatedly. So you might change the time on a directory multiple times as you do a compilation or so forth. And so as the entries in the journal get older and older, they tend to become stale, so they don't actually contain any useful information. And so by the time we get to the very end of the journal, that's maybe an hour old, most of the metadata we wrote out there isn't actually even dirty anymore. It's been since updated more recently in the journal. And so when we do have a directory that needs to be updated, we can take all of the updates that have happened to that directory over the last hour and build up one single large transaction and generate a single I/O that goes out to the object store and updates that directory. And so our overall write pattern that is random because we're updating these directories tends to consolidate writes over a long period of time to each directory and ship them out efficiently. So the overall aggregate I/O pattern generated by these metadata servers tends to be very good. One of the big questions is what actually gets put in the journal, and it's a trade-off. So there's lots of state in any complicated system like this, right? There's and what you actually do with that state is sort of a trade-off. So on the one hand, if you journal that state, it's expensive up front because you have to actually write to the journal. But on the other hand, it's very cheap to recover. When you restart the metadata server, recover from a crash, you read it in sequentially, and you get it all back. So that's expensive up front, but it's cheap to recover. On the other hand, if you don't journal state, you tend to have complicated protocols during recovery that have to recover that state. So some examples of things that you would journal would be the fact that you have client sessions open with particular clients who are accessing the file system, or maybe, of course, actual modifications to the metadata in the file system. Those things sort of have to go in the journal because they're important and you want to recover them later. On the other hand, things like cache provenance, I have a particular piece of metadata in one metadata server's memory, but it's replicated in other metadata servers' caches or in client caches. That type of information is very expensive to journal because there's a lot of it, and it's happening all the time. We don't want to generate all this I/O. So it means that as a trade-off, when we do recovery, when the metadata server restarts, clients have to reconnect, and they have to sort of resynchronize and reestablish this shared state in order to move on with their lives. But one of the key things that we do is what we call lazy flush. So whenever there are client modifications that the client is sending to the metadata server, the metadata server is queuing them up and is getting ready to send them out to the journal, but it doesn't necessarily have to do that immediately. It can send them out when the client does an fsync or after the write gets big enough and so forth. And then that makes the journal IOs larger and more efficient. The client protocol, where the Ceph clients are talking to the metadata servers, generally speaking, it's highly stateful, so we aim for strict POSIX consistency. So we would like two processes interacting with the file system to behave the same if they're on the same host, or if they're on different hosts. They'll just be a little bit slower if they're on different hosts, but that's sort of the level of consistency that we aim for, in contrast to protocols like NFS, which are notoriously weak in this area. The clients have a seamless handoff between metadata server daemons because they're actually using our own protocol and not sort of a legacy protocol like NFS. They understand the fact that they're talking to lots of different metadata servers, and they can behave intelligently as a result for that. So when the client is traversing the hierarchy, they'll sort of seamlessly move over to different metadata servers that are managing that part of the file tree, and so forth. And when the metadata servers are doing their load balancing and they're moving things around, they tell the clients about it, and so the clients can shift their cache state and so forth to actually have that work well. And of course, when they're actually reading and writing file I/O, they talk directly to the OSDs. So it's sort of an illustrative example of what this actually looks like. You have a client here, he's happy. He's going to mount the file system. So you'll do mount-t Ceph. The IP address is one of the monitors. That's sort of how you identify a particular cluster. So initially, there's going to be a few round trips to the monitor as he authenticates and gets a ticket that says, I'm allowed to talk to these metadata server daemons. He's also going to learn who the metadata servers are, what their IP addresses are, and who the OSDs are, and what their IPs are. And then there'll also be a couple round trips to the metadata server as he opens up the root directory. He opens up a session and then gets a handle essentially on the root directory so he can mount the file system. The metadata server is going to journal something to the OSDs because he wants to record the fact that he now has a persistent session open with this particular client. And then say the client traverses into a directory. So there are going to be a couple different round trips, a pair of round trips to the metadata server as he looks up /foo and then /bar inside that directory. If the metadata server had a cold cache, then he'll have to load those directories off of disk, so there'll be some corresponding I/O requests to the object store to populate the metadata server cache. But that's generally pretty quick. And then if the client does an ls-al, he wants to see what's inside this directory, there'll be an open operation. That actually has no interaction because he already has a handle and a lease on that directory inode, and so there's no MDS interaction necessary there. And then when he does the read to fetch all the directory entries, there's going to be a single round trip to the metadata server to fetch all these directory names. And again, if there's a cold cache, he'll load all that stuff off of a disk in a single I/O to load that directory in. But the reply is actually going to contain not only the directory names and leases that say they're valid until otherwise invalidated, but also all of the inodes that those names refer to, that the metadata server got for free because they're embedded in the directory. So that when the client does a stat on every single file, there's no additional metadata server traffic necessary. He already has it all in his cache, and it's all right there in the VFS, and he just plows right through it. And finally, when he closes, again, that's essentially a no-op here. And then finally, if the client is going to actually copy all the data in that directory to somewhere else, he now has all of the inodes for all those files and leases on those inodes saying that they're not going to be changed. And so he can go directly to the OSDs that store that file data to copy those objects to a local file without having any further interaction with the metadata server. So again, this means that the metadata server workload is very low and efficient. The client has these sort of highly stateful leases and all this prefetching and caching and so forth. And when he actually does start to do file I/O, he can spread that across the entire cluster and do it all in parallel and proceed on his way, and it's going to be fast and wonderful. One of the other interesting things that the metadata server does is what we call recursive accounting. So because we're essentially implementing a file tree from the ground up, we could do all sorts of interesting things. This is one of them. Essentially, for every directory in the hierarchy, we keep track of recursive statistics. One of those is the file sizes. So for each directory, we have a summation of all the file sizes nested beneath that point in the hierarchy stored in that directory inode. And so, for example, when you do an ls-al, the file size you see for a directory, instead of being this sort of meaningless number that's like a multiple of 4K or something on X3, is actually the sum of all the file sizes nested beneath that point. So essentially what you would get from a DU, but it's free. It's sort of accumulated over time efficiently by the MDS. We also maintain file and directory counts and the most recent modification time. So for example, if you dump the extended attributes on any of these directories, you can see all of these different statistics, which is interesting. And the key thing is that it's efficient. So whenever there are changes, this information is sort of being lazily propagated up the hierarchy tree by the metadata servers and stored. So it's not 100% time accurate, but it's way cheaper than doing a DU to try to figure out why your disk is filling up and what user is writing data and so forth. So pretty great for system administrators. One of the other interesting things we do is snapshots on a per directory granularity. One of the problems is that when you have a petabyte scale file system, you don't necessarily have a single data retention snapshot policy that makes sense for all the different types of data that you're going to store in it. And so instead, we empower users to create snapshots on any subdirectory, and that applies sort of recursively to things that are nested beneath that point. And we do this using a very simple interface without any special tools. So there's a hidden .snap directory. And if you want to create a snapshot, you just do a makedir inside this hidden directory with some random name, and that poof essentially creates a snapshot. And it has sort of the usual semantics where you'll notice if you look inside a subdirectory in the .snap directory, you'll see that it's also part of that snapshot, although the name is mangled to avoid collisions. And it has the usual semantics, so you delete a file, it disappears. If you look inside the hidden snap directory, it's still there. So it's sort of what you expect. And then when you're done with the snapshot, you want to delete it, you can just do an rmdir on that magic directory, and then it goes away, and it's sufficiently cleaned up on the back end. The file system client is implemented in a number of different ways. There's a native client in the Linux kernel that's been upstream for 2 to 3 years now that you mount with mount-t Ceph. You can re-export that as NFS or CIFS, sort of in the usual way. There's also a Fuse version of the client where it's implemented in user space but uses the generic Fuse API to mount. There's also a shared library that you can link directly into an application if you want to build something on top of the Ceph file system but don't want to actually mount it as a native file system on your kernel, then you can do it that way. And there are a number of things that we've done with that. So one example is there are patches to glue libcephfs into the Samba VFS, so you can directly re-export Ceph as CIFS without actually mounting it as a kernel file system. Another example is the Ganesha user space NFS server. Those patches actually support PNFS on top of Ceph, which is sort of an interesting thing. And another is Hadoop. So you can use Ceph in place of HDFS and run all your MapReduce stuff on top of Ceph, and you still get all the the localizing features where you run the computation on the same node that the data is stored on, and so forth. So it's very easy to consume. Sort of a picture of the current status of the project. RADOS, LibRADOS, RADOS Gateway RBD are very stable. People are using it in production. Generally pretty awesome. The file system is a bit more complicated. It's nearly awesome. There's a bit more sort of deliberate QA effort. And the story there is that I sort of bit off a lot initially. So I was working on this project for a long time sort of on my own and implemented all kinds of features in there with the snapshots and the recursive accounting and the scalability and so forth. And it's been being used for a long time, but it hasn't had sort of a deliberate QA effort that you need with a real QA team with all sorts of automatic regression testing and failure testing and so forth. And that's really what's coming over the next few months as we sort of get the file system in shape. So sort of just I don't know why my animations are all screwed up. A little bit about why we work on Ceph. There are limited options for open source scalable storage. There's Lustre in the HPC space. There's Gluster. There are things like PVFS and so forth, but there aren't that many options that really scale big. And that's an emerging requirement for things like public cloud and private cloud infrastructures in particular, and also for big data and so forth. And the proprietary solutions that people use instead tend to be very expensive. They tend to not actually scale all that well. They'll scale to like tens of nodes, but typically not beyond that. And also that scalability, if you start thinking about the money that you spend to actually make them scale, they tend to be a nonlinear function of your capacity as far as how much you actually have to pay to get the size that you need. And so for somebody who's trying to deploy a public or private cloud, there's really not a viable, affordable option that you can use to compete with, say, Amazon, which is frustrating. And the other sort of key thing is that they tend to marry hardware to software. You're sort of stuck buying a particular box running a particular piece of software. And so our belief is that there's sort of a paradigm shift that needs to happen in the storage industry where people need to have the same freedom that they have now with Linux and choosing whatever hardware they want to run it on in the storage space, so they can choose, the cheapest SATA drives they want or really expensive Fusion IO drives, and then run sort of a distributed scale-out system on top of that, and then go out from there. So Ceph was originally created at UC Santa Cruz. It grew out of some Department of Energy grants for petascale storage. After I finished my dissertation work, it was developed at DreamHost for several years, sort of as a skunkworks pet project of my own. More recently, we spun out a company called Inktank that's dedicated to supporting Ceph properly as an open source project, so that companies wanting to deploy this as a storage system can actually buy level 2 and level 3 support, consulting, performance tuning, that sort of thing, so they can actually run it in their environment. And there's a growing community. So the Linux distros are picking it up. There are lots of users. It's integrated with OpenStack, CloudStack. System integrators are looking at it. OEMs are looking at it as a basis for their future scale-out storage products. So it's exciting times. So that's it. What kind of questions are there? Yes?
Yeah. What do you do with hard links between?
Right. So yeah, that's always the question. So the observation is that hard links are rare. So we optimize for the case where there aren't hard links. But when there are, we have what's called a remote link. It's sort of like a symlink internal to the file system, but the inode is stored with one of the links, and the other one has to be able to find that other instance of the inode by inode number. And so there's an auxiliary table that essentially keeps track of parents of directories, and so that it can sort of recursively traverse the hierarchy to find that inode in the hierarchy. It's a little bit complicated, but it works. It ends up meaning that the cost to resolve a foreign link in that sense is a little bit more expensive. It's like login expensive to find the inode versus a typical inode table, which is sort of order one. It's a fixed cost. And so it's not that bad, but it's not quite as good. So for workloads where you have bazillions of hard links, this isn't necessarily the best choice, but it'll work.
So you might have to access another metadata server.
Right. Yeah, you might have to do a couple different lookups to find out where that inode is in the hierarchy and traverse to that point and find the inode. But that's something that the metadata server is sort of doing behind the scenes for you. Yeah. How do you deal with running out of space is the question. The easy answer is you don't. You generally, as the clusters start to fill up, you just deploy more storage nodes and things rebalance out of the way. Part of the problem is that we're using a hash-based distribution. So when you're writing a piece of data, you don't get to choose where the data is stored. The hash function does that for you. So the key is to make sure that the variance in the utilizations of different nodes is relatively tight. And so there are a number of features to actually make that happen. But essentially, once you start having devices that are approaching full, then an OSD map is published that basically says everybody slow down, switch to synchronous writes. And eventually, when it reaches a certain point, it says everybody stop writing because we're full. So. Yes?
So first of all, pretty cool stuff. I have
Thanks.
a question. How do you deal with the semantics of cross-directory renames?
Yes, so the question is, how do you deal with the semantics of cross-directory renames? So there's sort of two cases there. One is when the target directory is on the same metadata server. That's easy. You just journal it and update the trees and so forth. The harder case is when you're renaming across metadata servers, which sounds hard. In reality, the fact that we have this ability to dynamically move subtrees between metadata servers, and we're already sort of describing this distribution in terms of these trees that are mapped, we can sort of leverage some of that so that when we rename a directory somewhere else, we're actually only moving the inode. But then in the new location, it appears as if that subtree was then remapped back to the server where it already was. And so we're updating the subtree map and removing that one inode and updating the hierarchy. But other than that, there's not an expensive migration that has to happen to make it work. So it's complicated. There's several messages that go back and forth, and there's two-phase commits going on in the journal and so forth. But it works. It's just slower. That's one of the reasons why we try to maintain a coarse subtree partition so that most renames aren't across metadata servers. They tend to be localized in the same sort of part of the hierarchy. Yeah.
You mentioned early on about dealing with everything from cheap SATA drives all the way up to expensive in Fusion IO and VRAM.
Yeah.
Do you deal with having heterogeneous storage in the same group and you
Yes.
optimize for it?
So there are a couple of different ways to deal with that. So one is that the crush hashing algorithm essentially lets you weight each device. That determines proportionally how much data they'll get. So if you have drives that are twice as big as other drives, you just set the weight twice as high. And so they get twice as much data, and that's twice as much I/O. So that's the first answer. But that doesn't really deal with the different performance characteristics. So that's a bit more tricky. So the answer there is that the RADOS object model lets you create different pools of storage. So you might create one pool of storage that's based on slow SATA disks, and you put one type of data there. And you might create another object pool that's backed by Flash or something, and you put other data there. And then in the file system, you say this particular directory is mapped to this pool of storage. So /temp has one replica, and it's over here on this crap. And then /home has 4 replicas, and it's over here on this super fast SSD or whatever it is. And the final thing that you can do is in the crush rules that are specifying how your data is distributed, you can do something like say that I want 3 replicas of all my data. I want the first replica to be on this sort of fast tier of storage that's servicing both the reads and the writes. Maybe it's SAS or Flash or whatever. And then I want the additional replicas to be on this sort of slow storage that's all SATA and it's only getting writes. Unless one of the front end nodes fails, in which case we fall back. But that's sort of the exceptional case. So there are several different games that you can play to deal with it. Yes?
Okay, so you just mentioned one way that you have to do a little bit of additional configuration, creating tools.
Many opportunities.
The question I had is, you mentioned that replicas should be aware of their physical location. If it racks, if it's a row of racks. So how is that configured?
There are several different ways. You can have an administrator that sort of decrees this is the crush hierarchy that I want, and I meticulously figured out how that should be constructed and mapped it all out and said this is the map to use. The other way is you can tell each node in the ceph.conf file which rack, which row, which host it is, and then the startup script when it starts up will say, okay, I'm starting up OSD 712. Update the location for this OSD in the crush map to be in this part of the hierarchy, in this row, rack, host, whatever. And so it'll be placed in the right point, and then when it boots up and it starts getting allocated data, it'll be sort of in the right location. So that's sort of the direction that we're moving with. There's a lot of work going on right now with improving the integration with tools like Ceph and Juju and Puppet and all those sort of DevOpsy deployment tools to make it extremely painless to sort of deploy this on thousands of servers. And so that's one of the things. As long as you can tell each host sort of what their row and location is and so forth, then when you deploy OSDs, they'll dynamically allocate OSD IDs and they'll put themselves in the hierarchy appropriately and they'll start up automatically and so forth.
Okay, thank you.
Yes?
Do you have any plans to tackle geographical replication?
The question is about geographical replication. Yes. There are sort of 2 different projects there that are both on the roadmap, but they're a bit ways out. One of them is sort of disaster recovery type replication where you just want to have an asynchronous mirror that's sort of streaming off to another location so that if the primary cluster fails, you can have less than 5-minute old copy somewhere else that's in a consistent state. And that's sort of the easier of the 2. The other one is dealing with situations where you have an active data set that's distributed across multiple data centers, and you want to be able to tolerate an entire data center failure without having sort of a latency spike as you sort of time out and wait for that to happen. And that requires a different replication model where the client is actually writing to multiple data centers in parallel, and as soon as 2 of them reply, then the write is safe, and when you read from 2 of them, that sort of thing. And that's a larger challenge, but is also on the roadmap. So my time is out, so thank you all for coming. If you have further questions.